Good afternoon, everyone. My name is Pedro Garcia. I am working as hydrogen subject matter expert at Pipistrel Aircraft, and today we will be talking about liquid hydrogen fuel as an enabler of a novel sustainable air transport market. As a background, Pipistrel Aircraft is an aircraft manufacturer of ultralight aircraft and general aviation aircraft, founded back more than 30 years ago in Adriatic in Slovenia, where we have our main facility, Originala, for manufacturing, maintenance, and sales, and Pipistrel Vertical Solutions, the research and development branch in which I am working. We also have a state-of-the-art production facility in Gorizia, where we produce most of our aircraft. Pipistrel is internationally renowned for being the pioneer of development of electric aircraft. We have been working on electric aircraft since 2007, 15 years ago, with the Pipistrel Taurus Electro. And in 2011, we modified this design to include two fuselages, as you can see in the picture here. The Taurus G4, which was the world's first electric aircraft with 4 seats, winning an internationally renowned award by NASA. All this experience in research and development of electric aircraft allowed us to be the world's first aircraft manufacturer capable of type certifying an electric aircraft, the Pipistrel Velis Electro, back in 2020. Now, coming to hydrogen, which is the topic of this conference, the company has extensive experience in hydrogen research activities for aircraft, starting with the Hy-4 aircraft, which is a modified version of the Taurus G4 with gaseous hydrogen and with fuel cells that was flight tested back in 2016. This design was improved and flight tested again in 2020 in the Magepa project. And in the next months, we will be integrating a liquid hydrogen tank and flight testing this concept as well with liquid hydrogen and with fuel cells in the Heaven project, together with H2Fly and Air Liquide. Further, the company is researching into moving into the commuter aircraft segment with the Unifier 19 project, in which a 19-seater aircraft with liquid hydrogen fuel and fuel cells was designed and assessed in terms of market interests. So in the presentation, I will first speak about why hydrogen is interesting for aviation. Then I will continue presenting the specifics of the use of hydrogen in aircraft. I will continue the presentation with the main topic of this presentation, which is how liquid hydrogen can help fulfill Pipistrel's ambition to achieve a novel sustainable air transport market. And I will end the presentation referring to the industrial ecosystem needs that we need to make this ambition a reality. Well, first of all, a bit of background, the environmental impact of aviation. Back in 2005, aviation contributed to more than 5% of the anthropogenic radiative forcing, which is a measure of climate impact, produced by the whole human activities. Further, the aviation industry, although this trend has changed slightly because of COVID, is increasing roughly by 5% in number of passengers per year. And it is a hard to decarbonize sector, which will make that this, if no climate impact abatement measures are taken, this climate impact fraction will increase in the future. For this reason, the current 2050 goals have been developed that refer to a 75% carbon dioxide reduction, 90% NOx reduction, and 65% noise reduction of aircraft operations compared to year 2000. Now, if we look at how hydrogen could contribute to this, compared to the use of kerosene in gas turbine engines, we see that it is possible to completely eliminate the carbon dioxide emissions, and if fuel cells are used in the aircraft, it is possible to also completely eliminate the NOx emissions, and further to minimize the noise emissions compared to the use of a gas turbine. Regarding the specific role of hydrogen in decarbonizing aviation, unfortunately, aviation is a hard to decarbonize segment. One of the main reasons for this is the impact of the weight of the systems on the operating costs. There is a direct correlation between the maximum takeoff weight of the aircraft and the direct operating costs, so that the more an aircraft weight, it is more expensive to operate it, and it might make more sense to use other transport modes. For this reason, batteries with low energy density and low power density compared to gas turbine engines and to kerosene will be restricted to the use in general aviation and maybe in the commuter segment, as Pipistrel has been developed in the last years. Then hydrogen fuel cells and hydrogen gas turbine engines appear as an option for bigger aircraft. And when considering very long range, the use of liquid hydrogen is restricted because of the much higher volume of hydrogen compared to kerosene and the difficulties in integration, so sustainable aviation fuel such as biokerosene appears as an option. Pipistrel is developing mainly ultralight general aviation and wants to move in the commuter segment, so our activities are mainly related to batteries and hydrogen fuel cells. Regarding the specifics of use of hydrogen in aircraft, hydrogen could be used for fuel cell powertrains, in which a fuel cell would generate electricity for an electric motor powering a propeller, or in gas turbine engines, in which there would be combustion of hydrogen. Gas turbine engines have a higher power density, but fuel cell powertrains have a higher operating efficiency and no NOx emissions. Regarding the storage, this is the key challenge of hydrogen for aviation. Due to the integration constraints, the storage needs to ensure a high density of the hydrogen, and for this reason, liquid hydrogen appears as the dominant solution, of course with the challenges that are related, including the tank integration. In traditional aircraft, the fuel is stored in the wings, while in liquid hydrogen aircraft, the fuel will likely need to be installed in the fuselage, increasing the fuselage length. Now, after this brief introduction of hydrogen for aviation, the ambition of Pipistrel on hydrogen-powered aircraft is a product called the Pipistrel Miniliner for entry into service in 2030. The idea of this product is to have a 19-seater commuter aircraft capable of operating in grass airfields with short runway length, so that it is possible to use the infrastructure that is currently being used only for general aviation and not for commercial applications, to use it for commercial applications to connect regions of Europe that are not well connected by ground infrastructure. I will put the example here of the Aeroporto di Gorizia, which is a grass field located a few kilometers from here. This is an image from Google Maps that has a runway length of 1.1 kilometers. So the Pipistrel Miniliner would be capable of operating from this airport, opening a new node of operation that could transport passengers to an airport hub, like for example the Venice Marco Polo Airport, or to other villages that are not so well connected and have already this infrastructure, minimizing the investment in infrastructure required. Further, it is a must that this solution provides low noise. This is achieved via fuel cells and low noise propellers, so that there is no nuisance to the communities living close to the airport. And finally, to further reduce the infrastructure investment, the aircraft will be capable of performing several missions without refueling, so that, for example, it is possible to fly from the Venice airport in case it would have already a liquid hydrogen infrastructure, which is not expected to be available in all facilities in 2030, to fly to the airport of Gorizia and to come back without needing a refueling infrastructure in this airport. To back up all these affirmations, I will show here a market study that we did together with TU Delft and Politecnico di Milano for the Unifier 19 European project for the Miniliner, for a Miniliner concept serving as a microfeeder to the Venice airport. We show here the catchment area of the airports in which there could be customers interested in using this service for an 800-meter runway and 250 kilometers range. And as you can see here, this service could cover most of the region of the North Adriatic Hydrogen Valley, and this would be enabled by the use of liquid hydrogen. The studies show that for the Venice airport, including the Italian customers, there could be 20,000 potential customers and a demand for more than 80 million liners within Italy. Now, what do we need to, well, first, this is a render of, let's say, how this new transportation mode would work. It would be different from the traditional big airport that we are all used to use. It will be a service more similar to a bus that people use for commuting. And the idea would be to have a fleet of sustainable zero emissions mini liners operating between small airports and hubs, or between small airports, and serving communities that unfortunately do not have the ground infrastructure because of excessive investment required or other reasons. Now, what do we need from the hydrogen industrial ecosystem to achieve this ambition? First of all, of course, we need a low-cost, widespread, scaled-up, and green liquid hydrogen production and distribution. The hydrogen production will be scaled up by the demand from other industries. The problem arises from the liquefaction because it is more of a niche application for space applications or for transport of liquid hydrogen. So this needs to be scaled up so that the costs are competitive compared to kerosene. Second, the ground refueling and airport infrastructure needs to be developed, at least in the hubs. As I have said, the mini liner has the benefit that it would not require this infrastructure everywhere. But this would need to be developed further so that it is possible to operate this. Third, as it was said in the just questions and answers before, there is the need for novel regulations, standards, and means of compliance for system certification. And finally, novel liquid hydrogen storage systems and fuel cell powertrains for aviation that are lightweight and capable of operating at high altitudes are required to be developed by tier 1 suppliers to aircraft OEMs. Thank you for your attention.
Thank you, Pedro Garcia. I think time's against us, Pedro, so I'm going to thank you for your presentation. I think if we have one question from the audience, because I know Pedro has to leave us very shortly.
It's fine.
Any questions? Yes, sir, at the back.
Really interesting presentation. Thanks for that. One of the questions I've got around hydrogen being used as a liquid, I work in hydrogen refueling and presenting next. I'm really interested in what you think is a challenge, especially around the cryogenic, keeping it cold, because that's one of the things that we're seeing in the industry from transitioning from gas to liquid, is keeping it at cryo. Do you see that as a problem for the industry you're in?
So of course it is a problem in terms of logistics because in principle gaseous hydrogen can be stored for long times, if I'm not mistaken. But in the case of liquid hydrogen, zero boil-off solutions, that would be the solutions that do not lead to hydrogen venting during storage, are still in the development phase. Currently, well, as a curious, the information that I heard some time ago in a webinar that I attended, the NASA space shuttle, the NASA space programs, since they started, from all the liquid hydrogen that they bought, they were able to use only 50% of it. The rest was lost in these boil-off losses, refueling losses, etc. So for long-term storage, there is the need to develop zero boil-off solutions so that the logistics are improved. Also, for having the aircraft on ground, there is the need to better understand the hazards of having a system that can potentially lead to continuous hydrogen leak. This is something that, of course, is not desirable, and the systems will be designed in that way. But the bigger the thermal insulation, the heavier the system is, and the more expensive it is to operate. So there is a big trade-off there that needs to be solved within the industry.
Thank you. Thanks, Pedro. And thanks for pointing out once again that we have some of the technologies, but there's still a bit of R&D to do, and we will need to move forward with research. Thank you.